Yeah.
So you are
Is it
welcome
okay?
to present your study. So everything is fine.
Yeah. First of all, I am Dhananjay Kumar, a research scholar in Department of Mathematics, NIT Patna, India. And this is my joint work with my supervisors, Dr. Rajesh Pratap Singh from Central University of South Bihar, India, and Dr. R.K. Jha from Department of Mathematics, NIT Patna. The title of our work is Four Classes of Perfect Nonlinear Functions. These are the outlines of this presentation. First of all, this introduction where we will talk about some basic definitions and theorems, and then known classes of perfect nonlinear functions, and then a very important conjecture called Demboski-Ostrom conjecture, and that's after the application of perfect nonlinear functions, and then our proposed work as of perfect nonlinear functions, and followed by references. And suppose fq be a finite field, then a polynomial f over fq is called a permutation polynomial of fq if its associated function f is a bijection of fq, and these following conditions are equivalent for a function to be permutation polynomial, such as if the function is on 2, or it is 1 1, or equivalently if fx is equal to a has a solution for every a in fq, or fx equals to a has a unique solution in fq for every a, then in any one of the cases the polynomial will be a permutation polynomial. And it is very difficult to determine that whether a given polynomial is a permutation polynomial or not. So we have a very fundamental criteria to characterize this, that a polynomial called Hermite Criterion, and this states that a polynomial f is a permutation polynomial of fq if and only if f has exactly one root in fq, and for every integer t lying from 1 to q minus 2, where t is not congruent to 0 mod p, the reduction of fx raised to the power t modulo xq minus x will have degree q minus 2. If these two conditions are being satisfied, then the polynomial will be permutation polynomial. And actually this criteria theoretically, but is not so easy to practice. And is the linearized polynomial. Suppose f is a hello hello
So there is a problem with your voice, but is it okay now?
is it stable? Is am
Uh,
I audible?
yeah, it is
Hello.
not well, but we can understand your voice.
Okay, so may I continue?
Please check your connection. Please check your.
Just a minute. Let me check it.
Okay.
Is it okay now?
It seems okay.
Yeah. So let's continue. A polynomial effect over finite field fq of the form Lx is equal to summation alpha I x raised to the power q power I is called a linearized polynomial of fq, where the coefficients alpha i's are from the extension field of fq. This polynomial is called q polynomial or linearized polynomial, and basically linearized polynomials are linear transformations from fqn to fqn. And it is very obvious to see that fqn acts as a vector space over fq, and the problem that whether in which case a linearized polynomial will be a permutation polynomial. So the answer of this question is that a linearized polynomial is a permutation polynomial if 0 is its only root. And here we can see that this polynomial fx is equal to x square. This polynomial is actually a linearized polynomial over the field of characteristic 2. And a criterion to determine that a given polynomial, given linearized polynomial is a permutation polynomial, is that this determinant is non-zero, where the columns of determinants are the coefficients of this polynomial. And next, coming to the definition of perfect nonlinear function. A function f from finite field fq to fq is called a perfect nonlinear function, or sometimes it is also called planar function if this mapping delta fx, defined as fx plus a minus fx, is a permutation polynomial of fq for every non-zero a in fq. Here we can see that the polynomial fx equals to x square over field fq, where q is this form p power n and p is an odd prime. This will be a perfect nonlinear function because this difference polynomial delta fx is 2x plus a square, and this has a unique solution x is equal to b minus a square upon 2a. And looking to some important points about perfect nonlinear function. Perfect nonlinear functions are also called planar functions, and this equation fx plus a minus fx is equal to b for all a b in the field fpn or fq has exactly one solution. And it is very interesting to note that the perfect nonlinear functions can exist only over the field of odd characteristic, because if field is of even characteristic, it means if p is 2, then plus 1 and minus 1 are same in that field, and in this case if alpha is a solution, then of x plus a minus fx is equal to b, then alpha plus a is also a solution. And a perfect nonlinear function cannot be a permutation polynomial, since when we see that fx plus a minus fx equal to 0 will have solution and this will lead to the case that fx plus a equals to fx for some x in the field fpn, and this results, and this will produce a contradiction for f to be a permutation. So a permutation polynomial can never be a perfect nonlinear function. And here we have listed some known classes of perfect nonlinear functions over a field of general characteristic p. The first one in the list is x square, we have shown in previous slide. The next one is x raised to the power pi plus 1, and the third one is x raised to the power p power t plus 1 minus b raised to the power pk minus 1 plus multiplied with x raised to the power pk plus p raised to the power 2k plus s in the field fpn, where n is 3k and gcd 3k and 3 is 1, and k is congruent to s modulo 3 and s not equal to k, and n divided by gcd ns is odd, and v is a primitive element of finite field fpn. And the next one, and two more classes of perfect nonlinear functions are here. some perfect nonlinear functions over the field of characteristic 3 are given in this list: x10 plus x6 minus x square over the in the field f3n, where n is greater or equal to 5, and x10 minus x6 minus x square in this field f3n when n greater or equal to 5 again, and this is the x raised to power 3s plus 1 divided by 2 in f3n, where s is greater or equal to 3 is odd, s is odd, and GCD of Sn is 1. Next, talking about the equivalence of perfect nonlinear functions, then two perfect nonlinear functions f and g from finite field fq to fq are equivalent if there exist two linearized permutations L1 and L2 of fq such that this one g is equal to L1 composition f composition L2. And in previous slides, here these functions 1, 2 and 3 are actually inequivalent with all the functions in this list, but the equivalence of 4 with 5, 5 with 6 and 6 with 4 has not been studied yet, and this is to be studied. Next, we move to Dembowski-Ostrom conjecture. First, we see what is the Dembowski-Ostrom polynomial. So Dembowski-Ostrom polynomial is a polynomial over field Fpn, finite field Fpn of characteristic P of this shape: summation aij x raised to the power pi plus pj. This polynomial is called Dembowski-Ostrom polynomial. Actually, this was introduced by the P. Dembowski and T.G. Ostrom in 1968, and they used this type of functions to construct some projective and affine planes in finite geometry. And at that place they called this function the Dembowski-Ostrom polynomials having certain properties were called planar functions, and they conjecture that any planar function must be a Dembowski-Ostrom polynomial. That's after there are some progress about the Dembowski-Ostrom conjecture. In 1987, N.L. Johnson proved this conjecture for monomial xn over the prime field Zp, and in 89 and 90 several mathematicians, Ronai, Gulk and Hiramni, proved this for any polynomial over prime field Zp, and in 97 Coulter and Matthews produced a counter example over the field of characteristic 3, and we can see that this is the counter example: x raised to the power 14 over the field f34. This is a perfect nonlinear function, although it is not a Dembowski-Ostrom polynomial. In 2006, Coulter proved this conjecture
Professor
for
Kumar,
monomial.
your last 2 minutes.
Yeah, I am concluding very soon. Coulter proved this conjecture for xn and over p square and p4, but the conjecture is still open for p greater equal to 5 and n greater equal to greater than 1, and there are several applications of this perfect nonlinear functions. Perfect nonlinear functions are being used in cryptography in S boxes to resist differential cryptanalysis, and in semi-field and pre-semi-field we use actually a semi-field S is a ring without zero divisor and having identity element for this operation, and with left and right distributive. And if f is a do planar function, Dembowski-Ostrom type planar function, then this operation is defined with the help of our Demboski-Ostrom type planar functions. So having a Demboski-Ostrom type planar function will assure the existence of semifields, and in construction of affine planes we also use the planar functions. We can see that an affine plane is an incidence structure consisting of points and lines such that for any 2 points there is exactly one line through them, and for given line L and a point P there is exactly one line through P that does not meet L. And in our setup, in this case, points are the elements of FQ plus FQ, and lines are denoted as LAB, and if F is a planar monomial, a planar function, then an affine plane can be obtained as the points xy are on line LAB if and only if y is equal to f of x minus a plus b. So having a planar function will again give an incidence, an affine plane. So we use planar functions, perfect nonlinear functions, to construct semifields and affine planes in finite geometry. And these are two classes over the finite field of FP2M. We have proved these two to be a perfect nonlinear functions, and the third one is over the field FP3M, and the fourth one is over the field FP4M. This we have proved, and these are perfect nonlinear functions. These are the references. Thank you.
So thank you, Professor Kumar, for this interesting presentation.